this section, I may actually diverge a little bit from my slides because there are a lot of very good discussion. I think I have the liberty of coming almost towards the end. I think there are a lot of things that we can relate to as a EDA vendor, because at the end of the day, we're trying to provide a solution that will solve a problem. So a little bit about Jasper. Hopefully most of you have heard about us. For those of you who have not, so we're the leading provider of SoC design and verification solutions, leveraging advanced formal technologies. A little bit convoluted of a sentence, but it's very deliberate. Formal, I came into the picture in Formal about maybe 10 years ago. That's when I joined Jasper in the early days. Formal was used, I say, some of these myths at the time has a lot of truth to it. Again, just like Alex, I did not have formal background and coming into Jasper. So I came from design and verification background. So I'm relatively neutral, maybe biased towards the solution side than the technology side in the beginning. So what we do is that at the end of the day, Formal is a technology. We want to make it work for us. We want to make it solve verification problem. So that's, hopefully you will see at the next few slides that's how our approach and our philosophy that we carry on. Our users include architects, logic designers, verification engineers. So you can bring up teams, like what you saw in Ashis's, one of the categories, what are the users? And for many of these presentations, you can see that people use the tool from architecture all the way to post-silicon debug, so that the user do span. There's a piece of good news. Jasper is pretty much exclusively doing Formal. So we're not a company that provides many different technologies. So the fact that we're doing very well, I think hopefully that's an indication that Formal has been accepted in many cases. So we have our year-to-year exponential growth has been showing that Formal has been accepted by the public. So a little bit more, I just want to talk about where we are at. The second part, in the disruptive market opportunity, we believe that why do people adopt Formal? Sometimes you get evidence that okay, because based on my current project, previous project data, we can gain some productivity. We can solve $5 faster. But there are also cases that there are a lot of new problems that exist in today that may not exist 2 years ago. It may not exist last year. So it needs some disruptive technology. Disruptive means that it's inconvenient, it's uncomfortable, but it's necessary. So these are some of the areas that I think is very important to keep in mind. That not just about doing what we do previously better, but things that new challenges to rise up to it. So that's how we see things. And when we have our 10 of top 15 semiconductor companies, and strong financially, we have 35% of CAGR, stand for compound annual growth rate, since 2007. So in six years, we have been growing about 35% compound every year. So and profitable for 11 quarters. I'll skip through the rest. So talking about application, and people have mentioned whether it's some different applications, different apps. So here's what we have done since launching our apps-based approach. That we come up with these apps that can actually help different problems you can solve with Formal. Using Formal as a fundamental technology to really find the pain or the challenges that customers have. So that many of these apps, some of them are targeted, some of them is allow you to do bigger things. But there are also a lot of them is to be able to automate a lot of solutions. So earlier, someone, I think it was, I forgot who mentioned that. It requires courage to say that I want to use Formal. That's true in some, to tell the manager you want to do Formal. That's true to some extent. But there are cases that many of our customers that are using Formal under the hood. To them, it's a piece of black magic. I was doing something, X propagation. I said, I want to check that my design doesn't have access. I don't care if it's Formal or not. So to me, I don't have to justify to my managers that I want to use Formal. It's a flow that's set up of X analysis, a connectivity, control and status registers. To me, it's just a flow that I'm running. So I'm running Formal under the hood. Great. I want to see something. I want to explore my design. What James was saying that I have some microarchitectural spec. I do not know exactly what the outcome is. I ask the tool, show me an outcome. I didn't do any stimulus. To magically show me a trace. Well, is it formal? Maybe I don't care. So as a user. So then eliminate some of the justification part of things. So that's only one aspect, but I just want to bring them up. So I'm going to actually borrow the ARM's terminology because I really like this terminology, this AAHAA terminologies. Architecture, part of bug avoidance, bug hunting, bug absence, and bug analysis. I really like this terminology, and kind of it lands really well in seeing in the value part of point of view, not just about applications, because there are many dimensions that we saw. We have the user dimension. What are the demographics that we're approaching? What are the problem that aspect that we're trying to solve? Then, what are the values that we're getting? So, an architecture specification point of view, that in the beginning is usually an academic topics, but in the sense that some of the things that we presented, for example, architecture is the beginning of everything. From our point of view, let's say ACE is a protocol that will deliver to many customers, and so it's very important that the protocol itself is sound. So, and also important that to eliminate all the ambiguity. So maybe these are the areas that are very important to explore the architectural sense. Is it always the case? Maybe. It depends on the design. But avoidance, earlier people there are different presentations cover across similar things. When we say avoidance, is that if you can have a way to, whether it's for designers to very quickly, very early stage as they design something that uncovers any flaws in the design and correct it right there, so that the bug, if the bug is not seen in integration, you have a clean design, you have avoided a lot of bugs. Earlier, another presentation also mentioned that design evolved when from the beginning, the designer write it to the point when it's ready to integration. If you have a way to do a good analysis of the each evolution of the design, you keep the design clean, so that it will prevent a lot of problems down the stream. So that brings back to also another thing that interesting. People say, how do we show value? How do we sell to managers? What James is saying, how do we sell to managers? How do we make sure that the value are being observed? What has done earlier, that's one slide that I really like that you didn't go through a lot, is to show, I don't know, maybe glance through very quickly. There was two graphs that in Alex's slides. One of them show how the normal bug curve is. They go up and they go down. And the bottom, what he didn't say is that it's a graph where they pick the hardest block and really put a lot of formal effort in it. What the bug curve actually looks like, the bug is very high. In the middle point, it dropped to almost zero and maintains zero. That is bug avoidance, and that is value. That's undisputable value. So if you have this kind of information, take some trouble to track where you find bugs, what design is actually clean. It's the absence of bug. It's not about finding more bugs is good. Not necessarily true. The absence of bug means that it actually can show the tremendous value. So bug hunting, well, find bugs. At the end of the day, you still have to find bugs. Earlier, late. Bug absence is when we talk about what we approach and usually involve sort of, we call it deep formal, similar to what Tim had said earlier. I mentioned that do we prove something 100% true? That bug absence actually in the early days was the main selling point of formal. That was the main selling point. You have to do everything and get to foolproof, prove everything is correct. That's why I come into how do I know I have enough assertions? How do I know how far I'm approving? I'm running it earlier. That's another presentation was mentioning too. That we are running and running and running, and you didn't prove why. Is it a tool bug? Is something we didn't hide behind it? So that was the early days of today. As you can see, there are many other values that we're providing: the bug hunting, bug absence, but bug avoidance. But bug absence is still a very true area. Maybe today the goal is not to prove everything correct, prove all the properties 100%. Maybe there are 2-3 items that's very, very important to you. Maybe I have a second generation chip that added 2 new features. That's the whole purpose of having 2 generations, that 2 new features. Maybe I do want to put the effort in there. So it is it does require expertise. It does require effort, the real effort in there. But that's why what we recommend is that, pick your battle. There will be many cases that it's worth it to do the bug absence. Last but not least is the bug analysis. So as we see many cases, post-silicon debug is one example of bug analysis. So how do we know a specific item in there, and many of you, if you have the unfortunate case to have to do a post-silicon debug, it can be very painful because you're guessing, you're doing a lot of guesses, you try to collect as much information as you can. But it actually lands rather nicely for formal, because you notice the error symptoms, you see a failure. There is a failure, whether it's reported by errata or see it in the lab, you see a particular failure. So how do you help the tool come up with a scenario so that there are things that can be done to make it make the process more smooth? But this is one of the values that's definitely there. So designer adoption, earlier someone was asking about designer adoption as well, is that most designers do some level of verification. Maybe it's a sandbox testing that run some simple testing, and maybe it's about someone do a little bit more, trying to close maybe all the line coverage. It varies. What we provide, and you probably see this term too earlier, I think from James, visualize. What we do is that let's make this process smooth in two ways. The first is that it has to be better than just have to learn a lot of things. You say, oh, now use formal, but you have to learn, get good at assertions to guide the tool to the trace you want. And here's the formal engines, and it can feel a little bit intimidating. So what if, and this is one of the favorite that a lot of users didn't even care that formal is doing its magic. What if I ask you to say, instead of set a stimulus, tell me what you want to see about your design. You want to see a transaction to the memory. It's an output. Okay, ask the tool, and the tool will give you a trace. Then you can use the debug capability to trace you, is it what you expected or not. Forget about for a second how the tool do it. Forget that formal is doing its work. Black magic, whatever it is. Tell them the output what you want to see. The tool give you a trace. So make it as simple to and as easy as possible. It will help lower people's resistance. Then that's not enough. That's not enough. That we'll continue to enhance this kind of capability. Say, where do people get into trouble? They get into trouble maybe because they didn't have enough constraint. The trace is not good. How do we do that? Well, you can write constraint. Sure, one thing we need to do maybe make it very iterative. You can just manipulate one waveform and get the next waveform, next waveform. Maybe we have a way to make the traffic the minimum possible changes, so it avoids the possibility of violating an input protocol. So there are things that we are doing at Jasper to constantly monitoring customer what they're doing, where are the barriers, and continue to improve on it. That's why we cannot do the tools in a vacuum. We see what the problems are and help to solve them. So this kind of example, I'll skip through that. Next thing is about capturing properties. If I can see a trace of my design at work, it's easier for me to think through what are the assertions I can do. Even though assertion itself is not, I always argue that it's not that hard to write. Some people will say that it's hard. I really don't think it's hard. To come up with what assertion to write sometimes is hard. Say, oh, write me good 100 assertions in your design. I don't know where to start sometimes. But if I see my design in action, highlight on the design, dumb up assertions, maybe that's not that intimidating. Then once I have also the design is not always a signal level event. It's about event level. An event could be a transaction. Start with a valid and end with a ready, and for the address space followed by data space followed by whatever. A series of events create a transactions. And when we look, maybe when I do it, explore my design, I see that the faces, I highlight them, I put a label on them. Then I can build. Then it allows me to build on those events. Now I have an address space. This represents address space. This represents data space. I highlight this, followed by this. It's a transaction. So this also allowed the designer to be able to explore the design very effectively, no longer by signal level. So talk a little bit about end-to-end properties. This is about bug hunting and bug absence. It really depends what your goal is. Maybe you want to do bug hunting, maybe you want to do foolproof. Bug hunting is, the end-to-end property is about trying to step back, say that I really, for a moment, let me forget about how I, the designer, or whoever the person that I'm the verification engineer, the designer, how they implement it. But what is its purpose? What does it want to do? If we can prove that it's true, then the chance of me missing something fundamental is low. I could have write a lot of low-level assertions, but I can't really tell that I'm getting what I want. Earlier, one example from Tim is interesting. So, a FIFO, for example. How many assertions do I need for a FIFO? Depends on what kind of FIFO it is. You write the pointer is correct, no overflow, underflow, and what if I verify the FIFO behave like a FIFO? What is a FIFO? Data goes in, go out as the right order, no drop, no duplication, no corruption. Let's say I step back and say I have a design that's supposed to do that. I'm functionally correct. If I prove that, then I have less worry about the pointer is correct or not. Maybe it's different clock domain. The input and output clock is different. Or is the clock being synchronized correct or not? So if I can step back and do high-level properties, I'll be a better chance to meet my microarchitecture spec. So scoreboard, you've seen it many times, so I'm not going to go through that much. So now, high-level property sounds like a good idea, but there are problems. First of all, it's not always easy to write, and sometimes it's not always easy to prove, because you're dealing with a bigger space right now. So what do we do at Jasper? It's a combination of methodology and technology. So how do we make it easier? We create some of these common high-level model like scoreboards, maybe a cache model that we can verify that the cache is set associative. We have some high-level macros that create the high-level requirements for you. So the designer, the people can just hook it in. But there are other techniques that, like what Alex mentioned, that maybe you want to do some assumed guarantee ways. Take a design, black box, replace it with some requirements and make sure they're guaranteed. So these are methodology. Leveraging symmetry. A bus is 32-bit. I want to verify 32-bit go through enough correctly. Maybe there's symmetry in there. Well, maybe I'm not a formal person. I don't know what symmetry means. So the tool maybe give you a capability to check bus symmetry. Say, oh, there are only 4 segments. You only need 1 bit for each bus. So these are the things that we provide to give user hints how to effectively handle this complex problem. Last point I want to make here is that in the old days, when people, not old days, even today, when people do theorem proving, there's a lot of abstractions that people use. Abstractions can be hard and not natural to simulation people or anybody for the matter of fact. So what we do is we try to do a lot of safe abstractions under the hood so that the user just know that the effect of it doesn't have to do it. And that's one point I want to make. A safe abstraction is not always easy because, let's say I want to abstract counters. Counters have so many things, possibilities. How do I safely abstract a counters? That's when I can take credit for some of these things because I come from a design background. I didn't come from a formal background. So when people tell me counters cannot be just abstract, I say, no, but in design, we don't care about counting the half-life of some mechanism for something. I care about what counters we see in the design. I can claim there are only 3 types of counters, and I'm not going to go into detail. If we can abstract these 3 types, we just handle that kind of problem. So have that kind of point of view to step back to see what are the things that we are facing. And even though we limit the scope to the things we do, handle 90% of the time is actually a very good solution. So that's how we see things, is that how do we address this kind of problem. So the big picture, in the architectural cases, one of the things that we have, one of the new capabilities we have is deadlock detection. Deadlock, in the architectural sense, when you have multiple systems combined to subsystems or different subsystems, indirectly there's a dependency loop in there. It's very difficult to find. And usually you find it in the lab, or you find it very luckily in system level simulation, and you couldn't figure out why it happens because it takes 3 days to finish. So, but knowing this type of characteristic, the tool can actually do a lot to help create internal, we call it helper assertion like lemmas, or track where the traffic is and track where the loop is. So this is a problem statement. So that's why it's our job to try to take a problem statement and see what we can offer to solve the problem. So that's kind of how our approach is. In the architectural point of view, a deadlock can come in 3 phases. It could be architectural bug. It could be an implementation bug. Actually, interesting about the other day I was explaining, when people verify, that's a cache coherency problem. When we work with customers, if you can verify the architecture is cache coherent, then in RTL you don't need to verify that the RTL is coherent. You just need to make sure the RTL obey your architectural requirement. Then RTL is coherent. That's not the same for deadlock. If my architecture is not deadlock free, RTL most likely would deadlock. But even if my RTL or my architecture is deadlock free, RTL add dependencies, because that's what RTL does. You do more dependency. Then that's why architecture itself is not sufficient. My implementation bug can cause a deadlock. And last but not least, my system integration can cause deadlock, because right now I have different subsystems not mutually dependent on each other. So having a solution for separate one big problem into multiple solvable problems is another approach that's very important. If I say, try to solve for me deadlock problems, nobody in the right mind to say, yes, I have a deadlock solution for the deadlock problems. It doesn't exist. But let's break it down. Deadlock has 3 main causes that cover 95% of the time. Let's make sure we solve all 3. So that's kind of another approach that we have done. System level deadlock apps. Actually, I'm not going to go through that for interest of time. Now, am I done? So this is an interesting topic everybody is talking about. So this is now about coverage. Coverage, we have multiple discussion, debate, argument, whatever that is. I mean, it's going to go on for the next 5 years. The people is not going to totally agree, but here's where our point of view, what we can do. So there are 3 use cases. The first use model is that I want to make sure that my constraint, I have a constraint, I have assertion. Okay. So I want to make sure that my constraint is not over-constrained. I want to make sure that my assertions cover sufficient space. So that's first purpose for coverage. Second thing is that now I didn't get a full proof. I got a bounded proof. So a bounded proof of k cycles. What does that mean? How much have I done? Second thing is about getting credit of a bounded, short of a full proof. The third is accelerated closure. I think you've seen many of these things in part and pieces in other presentation as well. Is that I have a simulation test bench. I simulate something, and I got some coverage information. Maybe I'm able to reach 90% coverage, whatever the coverage means. Could be line, code, functional. Maybe Formal 2 can help me. In what way? Maybe I can read in the database, just like some of the which coverage holes are not really a hole. Why is it not a hole? If something is not reachable by Formal, it cannot reach by simulation. So maybe that will reduce what 100% means. So at the same time, actually, at the same time, the tool can also, because our technology, try to map the different technology to be able to generate something sensible to give suggestion for the one that can be covered. So I don't want to simplify things. In the ideal world, whatever cannot cover, the tool prove that, okay, this one cannot be covered. It's not a hole. Whatever can cover, here are the vectors, done. Doesn't in the non-ideal world, doesn't work that way. Most of the time, your test bench, your DUT may be in the different design hierarchy, and as you run in Formal. Just because Formal can give you a trace doesn't mean that in the system level is correct. So there are other problems. So how do we solve those? There are several approaches we'll solve. I won't go into detail here. We do have a property synthesis capability that can actually extract assertion and constraint from the system level test bench into the block level, so that whatever trace you do at least meet those requirements. So these are some of the ways that we help close. So this the 3 use model, we're trying to get coverage. I mean, I won't get into the detail about how we cover them, but the metric has to be, whatever metric, whether you agree or not, it has to be consistent, and it has to be easily comprehend what it actually means. When I say something is covered, what does it mean? Does it mean that it's in my conal influence? Maybe that's too generous. So, and there are other ways to make sure that even if the conal influence doesn't matter or not, like mutation is one of the ways. It's not the only way. It's a decent way with some cost because of the thing. But there are things that the tool knows. Because when the tool analyzes it, there's certain expression that was embedded in the equation. So we know what part actually matters for the properties. Even there are a lot of logic that even if it's in the conal influence, does not affect the equations that we know that it's actually outside of what we can check. So there are things that we want to be conservative. You know, if we don't, something that's not really covered, we should not say is covered. And then the caveat is that formal simulation doesn't map exactly this. That's why it's important to understand what they both means and knowing how to complement each other. Last point about formal is that, as you can see very clearly, formal should not be all or nothing. I do formal for all this block, or I don't do formal at all. It doesn't work that way. I think it should integrate very well with everything else you are doing in your verification environment. So some of the new apps that we have done, so let's say things has changed. You know, low power used to be something that you do in a very, very small handful of high-end ICs. Today is everywhere. Low power become a problem. An issue that affect everybody. Multiprocessor used to be in supercomputer. Now it's, and everybody's cell phone probably have multiple processors. Security now is implemented partially in hardware, partially in the software. So we have to adapt to solve the problem accordingly. So how, you know, we provide some new apps that solve these kind of new problems. Right? I'm managing my time pretty good. Okay. Yeah. Yes. Question. Do we have any questions for Lawrence? Oh, actually, you just sit down in front, actually.
So you said mutation is not the only way for coverage. What are your other thoughts? What are the other things we could do?
So mutation find out if some problems, some changes will not propagate to your properties. So that's a functional path. To just because something it has a structural path doesn't mean that it has a functional path.
Yeah, but the mutation-based thing exercises the functional part, right?
One way of exercising a functional. If I stuck at 0, stuck at 1, invert. You know, so there are many possible. Even just because maybe stuck at 1 is not a problem, stuck at 0 is. You see what I'm saying? So it's one of the ways, but it's not the only way.
So I agree with you that mutation-based analysis is a mode of completeness analysis than a conventional way of looking at coverage. But what are the other things that you think we could do? I mean, is it something you could share right now, or is it tied to the tool?
It's tied to the tool, but I can share a little light on some of the things we do.
Yeah. Okay.
So if I have some logic that is in the conal influence.
Yeah.
Structurally, there's a path from the conal influence to that part.
Mm-hmm.
If the toggle of the information doesn't toggle functionally to impact the output, that point is actually not covered by the properties. So you can actually, in the conal influence, there are many ways to abstract the analysis region per se. We have many ways to abstract the analysis region. That's great for filtering out things that are not really covered as in the analysis region. So that's one of the ways of filtering it out. So it does involve some set equations and analysis.
So you do the toggle on the inputs of the driving, of the logic that is driving, but you do a conal influence based.
The true conal influence, the true conal influence.
True conal influence, functional, semantical conal influence.
Yes.
You do.
Yeah.
Okay.
That's one of the many ways.
Any more? No? Okay.
Right. Thank you.
Time anyway. So thank you very much, Lawrence. Thank you.